Now that we have our Leontief input-output model derived, we may want to ask, how is it possible to meet certain demands? And if we recall, this set of entries here represents our consumption matrix, our C matrix, that tells us how much of each industry manufacturing will need to consume per 1 unit of output, how much of each industry agriculture will need to produce per 1 unit of output, and same thing for services. Now we've already mentioned that there's going to be X1 units of manufacturing produced. And again, this is going to be some sort of, typically some sort of dollar amount, or millions of dollars, billions of dollars. X2 will be the units of agriculture produced, measured in dollars. And X3 will be the number of units of services produced, measured in dollars. And so what we know from this is that if manufacturing produces X1 units, then we're going to have to take this first column and multiply it by X1 in order to calculate the total amount of manufacturing, agriculture, and services that need to be produced just to satisfy the manufacturing output. And similarly, agriculture is going to produce X2 units of output, and it's going to require 0.4 units of manufacturing, 0.3 units of ag, and 0.1 units of services for every unit it produces. And then the same thing for services here. And so we can of course write this as that matrix 0.5, 0.4, 0.2 times the x1, x2, x3 vector. And then we're saying that on top of that we're going to have some sort of demands. And these are going to be the demands placed on each of those three sectors. So this could again be maybe our town's demand. And we ultimately are producing to be able to serve a customer, but we also have to make sure that we're able to function as an interconnected set of industries. And so that will tell us the total amount of manufacturing units produced, agricultural units produced, and services produced. And this gives us that ultimate equation, which is that the vector x equals the consumption matrix multiplied by the vector x. Now, one thing we should keep in mind is, this is an odd thing that the output depends on the output, but one thing that we should note is that c times x should be smaller than x. If it's bigger, then that means that it's costing us way more. For example, to produce 1 unit of manufacturing, suppose that it cost us 2 units of manufacturing to produce 1 unit of manufacturing. Well, that wouldn't make very much sense at all. And then we have our demands by the town or whatever industry. And what we want to do is we want to solve for x. That's our next task, is solve for x. How much should each company produce in order to meet its intermediate demands, as well as the final demand? All right, well, so we're going to use some matrix algebra here. And the first thing I'm going to do is, much like I would in an algebraic setting, I'm going to isolate the x vector, and that is equal to d. Now I've got to be really, really careful here, because I can't reorder vectors and matrices, because I'd be destroying the dimensional requirements of that process. Now, one thing that might be tempting at this point is we could write undistribute or write factor, but I don't really have anything here other than a 1. So if I actually factored out an x to the right, which is what we are going to do, then as of right now I would have 1 minus c inside the parentheses. But 1 is a scalar, and c is an n by n matrix, in this case a 3 by 3 matrix. We simply can't do that. So the fix for that, we want to make sure that this component and this matrix have exactly the same size. So one matrix that I could create that would be 3 by 3 that would not change the result would be the identity matrix. And now if I have I minus C in here, and this is 3 by 3, and this is 3 by 3, then their difference exists and everything works out perfectly. All right, so we're almost there. We have equals D here. And now this quantity inside the parentheses, this right here, if I for a moment just think about that as some matrix, I'm going to call that maybe matrix B, capital B. And as long as, and the reason I'm writing that is because when we see I minus C, we want to think about it as two separate matrices. And it is, but it's the subtraction of two matrices, which results in just one matrix. So we're going to refer to that as B for the moment, and then we'll replace it with I minus C in just a second. So we're B, as long as B inverse exists. Well, what's the first condition that we need for B inverse to possibly exist? Well, it needs to be an n by n matrix. And since in this case, it's the difference between two 3 by 3s, it will also be a 3 by 3. Now that doesn't mean the matrix is invertible, but that's the first step. So the first thing to require is that it's a square matrix. Okay, so we're going to make the assumption that it does exist. And there could be situations where it doesn't, but right now we're not going to worry about that. So our equation as of now is B times X equals D. And as long as B inverse exists, then what I can do is multiply both sides by the inverse of B. And so the product of a matrix and its inverse gives me the identity. And then I get the identity times X. Well, that's a matrix transformation. We're taking a matrix or a transformation matrix and doing a matrix vector multiplication with the vector X. Well, since it's the identity matrix leaves a vector as it is, and so X is equal to B inverse times D. Well, what is B? B was this quantity I minus capital C. So all I'm doing here is just replacing B with it. Now we could have left it there in the first place. We could have just said multiply both sides by quantity I minus C inverse, and everything would have been fine in that regard as well. But here we go. Here is our solution for figuring out the total amount needed to be produced in order to meet a certain demand requirement. So as an example, let's say that our final demand for our demand matrix above, let's suppose that we needed to produce maybe 1,000 units of manufacturing, 750 or 7,500 units of agriculture, and maybe only 800 units of services. So here's the consumption matrix, and we are trying to solve for X. So right now we know that X is equal to the difference between I and C inverse. Okay, so the first thing we'd want to do is to form our I minus C. And we want the difference between these matrices, we want the inverse of that right there, multiplied by D, which is the 1,000, 7,500, and 800 vector. Now, we got to be really cautious because the inverse of a difference is not the difference of an inverse. You cannot apply the inverse to the two matrices individually. That only works with products, and even with products, when we take the inverse of A times B, we multiply B inverse times A inverse. So we cannot do this manually. We'd have to do this in some sort of calculator. So let's just take a moment to reduce this down just a tiny bit. We're going to eventually interpret what the inverse matrix means in the context of this particular problem. But when we take this difference and we have 1 minus 0.5 giving us 0.5, and then we're subtracting, we're taking 0 minus these values here, so we'll have negative 0.4 and negative 0.2. Then we'll also have negative 0.2 here. We'll have 0 minus 0.2, 1 minus 0.3 is 0.7, and 0 minus 0.1 is negative 0.1. And then the last row we'll just have negative 0.1, negative 0.1, and positive 0.9. And we want the inverse of that multiplied by 1,000, 7,500, and 800 as our final demands that we're requesting. So one of the things we should see is in our solution, when we come up with the answer, this answer better involve quantities that are greater, probably far greater than the 1,000, 7,500, and 800, because how could we possibly meet the final demand if we produce less than the final demand? We still have an entire set of industries to satisfy in the intermediate demand. So one interesting thing to think about here is these diagonals that were actually changed not only by becoming negatives. You can kind of think about these as what is left over for each. Remember, this was manufacturing and what they required in terms of production of 1 unit of its output. So they needed to consume 0.5 units of its own product in order to produce 1 unit of output. So it's almost like saying, in order to make $1 of manufacturing has to spend 50 cents of manufacturing. So this 0.5 can sort of be thought of as what's left over to be able to satisfy the other intermediate demands and the final demand. Same thing here, the 0.3 is how much of its unit it's going to use up. And then it has, of every unit it produces, it has 0.7 of that unit to be able to share with the other industries as well as the external demand. And then same thing here, services is the lightest in terms of using its own product. So it has essentially 0.9 of its unit to share with the other industries as well as in the final demand. Now these negatives, you can almost think about these as how much is going to be used or consumed. So let's go ahead and calculate this product. Now there are many calculators out there that will do this. My preference is to use one that I know that is consistent and I can be flexible with. And here at the time of this recording, I'm using Wolfram Alpha, and to enter there's my C matrix right there. You can see that to open and close the matrix, we need these pairs of brackets. And then when you click on them, you can kind of see where they open and close. So that's the C matrix right there, or rather the I minus C matrix. Then each row in that matrix requires a pair of brackets, and you can see that 0.5, comma, negative 0.4, comma, negative 0.2, that's the first row of our I minus C matrix, comma, and then we're going to start the next row, and the next row is negative 0.2, 0.7, negative 0.1, and then of course the third row, and then we close the brackets. To do an inverse, we can just do to the power of negative 1. Now that's not actually going to raise it to the elements to the negative 1 power, that means the inverse of. Gotta be really careful there. To get a vector, what I have to do is create a matrix, and each row is only going to have one element in it. So the first row is just 1,000, the second element is 7,500, and then the third element is 800, and then we close our matrix. The easiest way to check is whenever you press the equals button, you can see whether it's interpreted your values correctly. So according to this, manufacturing will need to produce $16,731.50 of product. Now the final demand was only $1,000 worth, but there's a lot of consumption of manufacturing. And a similar case for agriculture. Agriculture tends to have more of its output left over. So it is the 7,500 and the 16,000 are closer together than the 1,000 and the 16,000. Remember, this was manufacturing used up a lot of its own product. And then here we can see that 4,541 is even closer to the final demand. And that's again because a lot of what services produces is actually available for intermediate demand and for final demand. So that's how we go about solving this Leontief input-output model. And in the last video, we'll just try to make sense of this inverse matrix, because a lot of times inverse matrices actually have a really important meaning. And so for this particular sector, we'll go ahead and take a look at what this I minus C inverse matrix actually tells us.